Hello, intro to psych class. Because of the inclement weather, they've canceled classes. And because this is a second snow day, we've fallen rather behind in our materials. So given that you now have some free time today, when we should be having classes, I decided to make a video lecture to catch us up so we could get back on track. Okay, so as you can see from the syllabus schedule here, we should be at consciousness and sleep at this point, right? That's the 20th today, or whenever you're watching this. Um, but we're stuck at the last part of vision. We haven't gotten to non-visual. So in this particular video, we're going to cover in the rest of vision. We're going to hit the non-visual systems for sensation and perception. And then I will make another video where we look at consciousness and sleep, okay? And so we should be caught up by then. So let's get rid of this. Without further ado, let's pick up where we left off, okay? So if you recall, I had you all stare at this flag for a short period of time. Then you get an after image is what it's called. And many of you saw the American flag. Okay, so we were talking about the Young-Helmholtz theory of color perception, but it doesn't explain all of our color perception. Okay, so we're here to fill that gap. Now, the opponent process theory explains why we see after images, and it helps to explain the rest of color vision. So what the opponent process theory proposes and has found is that there are pairs of visual neurons that work in opposition of each other. In other words, there's an opponent process of these opponent cells in the retina. Okay, so for instance, we have our red cones and things like that. But if you have some kind of red or neuron, excuse me, this opponent process cell that's excited by the color red, it will be inhibited and essentially not respond to green color. So in other words, red green cells are excited, they increase the firing rate, as we know with neurons, right? So they'll be excitatory in response to red wavelengths, whereas they will be inhibited by green wavelengths. Okay, so then there's decreased firing. And so this is how we're able to see colors, even if we might be deficient in red or green, okay, or blue. Same thing goes for blue-yellow opponent process cells. They might be excited by blue wavelengths, but then they're inhibited by yellow. Okay, so then if yellow's present, right, that's being inhibited. That's how we know that we can see yellow, right? So this helps explain why people who have a red-green deficiency can still see yellow, because when they perceive the color yellow, their blue-yellow opponent process cells are being inhibited, and our brain interprets that as being, that must be yellow because that's the opponent of blue, right? It's being inhibited, it's not being excited. If it was being excited, bam, we would have blue. Okay, and same goes for white and black. Okay, so opponent process theory talks about how one of these cells, right, these cells will be excited by one color, but then they're inhibited by the opposite. Okay, and so this helps explain why we can see that yellow if we've got that red-green deficiency that we talked about last time. So, right, some other examples, some cells are excited by green, inhibited by red, like I explained up here. Some excited by blue, inhibited by yellow. And let's get to that after image then, right? So we have the image that I made you stare at, and it had this yellow block here and these kind of grayish stars in between, and same gray bars in the place of red and green in the place, or excuse me, yeah, and green of white. Okay, and so what you see, or what happens, is when you stare at something long enough, your cells start to get tired. Okay, so what happens is we will be exposed so long to, for instance, let's say the yellow. right? And we're exciting, or I guess you could say inhibiting. We're inhibiting these cells for a long period of time. What happens when you stare at a white blank kind of screen like I did before is there's this fun rebound effect, okay? And so you'll now see the opponent process because your cells are kind of being excited, even though there's an absence of blue there. And so it kind of just shows you the opposite color that was either being inhibited or excited. And that's why you're able to see blue in that after image. Okay. So interestingly enough, this is helping to explain the other piece of color that we couldn't explain with the trichromatic theory. Okay. You see that opponent color when you're staring too long. And some examples, right? Yellow goes to blue, green goes to red, etc. Okay, so to sum this up, right? The trichromatic and opponent processes are complementary theories. So it's not that either of them are wrong. It's just that we need two theories and there are different mechanisms for which we see different colors. Okay, so there's kind of a two stages of color vision going on here. Your retina receptors for red, green, and blue respond to different color stimuli. That's the trichromatic theory, right? So that's what we talked about before. They're definitely sensitive to those colors. However, these signals are then processed by these opponent process cells. And so what it'll do is, right, we're exciting one, maybe blue, 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 gets excited, but that's inhibiting yellow, so we're not seeing yellow, right? And say vice versa, if yellow is exposed, an inhibitory process is going on, and so we see yellow, not blue. Okay, so this nicely explains our color vision using these two theories. Okay, let's talk about some other features of how we process information visually. Right, so we can see color. We talked about how the eye transmits a message and how we see color. So now let's talk about some more specific kinds of abilities of our eyes. So how we detect different features of things. That is, how do we detect, various shapes and things of our scene, right? Textures and all that fun stuff, because it's not just all kind of flat. So there are these things called feature detectors, which are specialized neurons in our occipital lobe. Remember where that is, right? And so what we see with feature detectors, with these specialized neurons, is that there are these, clusters of neurons basically that specialize in seeing certain things. Like they are able to detect shapes and lines, angles, and movement. Okay, so we have specialized cells, these feature detectors, that detect these features, shapes, lines, angles, and movement. Okay, so for instance, there's a classic study with toads that was done by Ewert and his colleagues. Okay, so toads tended to respond, let me get a little color here, to respond to these kinds of certain kinds of lines. Okay, so what they would do is they were able to um, detect when toads were stimulated in the mind, okay, in particular areas where these feature detectors were. So sometimes they would show them a line that maybe went parallel, right? Or they showed one that went perpendicular. Okay, and so toads tend to, in certain areas, in certain feature detectors, tend to be more responsive to these vertical lines, these parallel lines, okay? They tend to care more about parallel lines that might look like they're kind of moving upwards, okay? And the reason behind this, you might wonder, why they don't care so much about ones that are laying this way is because they think, at least for these particular feature detectors where they detected this, these lines simulate worms and how worms move, right? Maybe, these guys are low to the ground and you can kind of see how low they move. Okay. If you want some more information about feature detectors, go to this website on YouTube. Okay, and they're going to talk to you about a very classic experiment done with cats and shapes, like, excuse me, with lines, sharp edges. Okay, and so cats are rather attuned to that as well. Okay, so there we go. Okay, so let's talk about something related. There are also things called super cell clusters. Okay, so these are a little tricky. They're similar to feature detectors. Okay, so feature detectors are more about, right, detecting shapes, lines, angles, and movement, these features of things, right? This kind of angular piece of the frog, for instance. Supercluster cells are clusters of cells, as the name suggests, and they get information from these feature detectors. Okay, so they collect more information as well, but they're important in complex recognition. Okay, what do we mean by that? Stuff like faces, right? So I gave you all the example at the beginning of sensation perception that Oliver Sacks, he was unable to recognize familiar faces. Okay, so a part of his fusiform gyrus that's located in the temporal lobe near your right ear was not working in some kind of way. Okay, so he was unable to recognize, faces like of his wife or whomever. And so supercells are really interested more in complex recognition, right? Because a face does have shapes, lines, angles, movement, color, all sorts of things. And it helps us to remember, people that we see every day, all the time. Okay. And finally, one last piece or one last word on how we kind of process some visual information in terms of features and picking all this up. This is all occurring in parallel. Okay, so in other words, our brain does parallel processing whereby we see color, motion, form, and depth, right? And it's all separated. We have superclusters, we have feature detectors, and all of these things come together and we put it all together to see one figure, right? Maybe this frog or the screen that you're staring at now. And so it's detecting shapes, lines, and it's able to, through parallel processing, bring all of this information together for us, right? So the proper definition, or a more formal definition for parallel processing, is the process by which we process many aspects of a stimuli at once, right? So the brain subdivides some visual scene, color, motion, form, depth, and then we construct our perceptions by integrating all of these pieces, right? This is bottom up, right? So our brain's doing some bottom up stuff, but then other things tend to influence our vision. Okay, so let's move forward and talk about depth perception. So there are a couple of features that allow us to see depth. Okay, so we're going to be talking about several of them. So generally speaking, we transmit a two-dimensional image. We project a two-dimensional image to the back of our eyes. That's what's actually happening in our eyeballs. It hits the retina, and then our brain interprets it as some kind of three-dimensional thing, right? So we know from studies that our perception of death is partially innate. So at some point, when kids start to crawl in particular, we notice that they know about depth. They understand it. Okay, so how do we know this? Through visual cliff experiments. Okay, so at Cornell University, Gibson and Walk, some researchers in psychology, developmental psychologists, they placed 6 to 14-month-old infants on the edge of a safe canyon. Okay, so you can see the baby right here, right, is on some kind of like patterned surface, and then all of a sudden it goes clear. We know from the reflection that there's a piece of glass there. Okay, so they popped the little baby here, mom's over here calling to baby. Okay, and so half of the surface is kind of regular, the other one gives the illusion that there's nothing there. And so you can see down here they put the same pattern as up here to kind of trick the baby, right? Because if baby doesn't have depth perception, they're just going to crawl all the way across because they won't realize that this is further away than this visually, right? This is going to look different from being up here versus being this close to baby. Okay, so this is the visual cliff experiment. They want to see if kids will stop or if they'll continue on. And so what we find is most infants, when prompted to crawl over this clear part, won't. They'll refuse because they get depth. They understand something's going on, right? This is way down here, and they don't understand glass yet, right? Like they're not into that. But they know that this cuts off and all of a sudden it drops off. And so they're hesitant. They're not going to walk across it. Okay. So we know depth is partially innate, right? And so we're going to talk next about different cues to how we know the depth of certain things, right? Distances and stuff. So how we actually perceive it, what's going on in our brains. First off, we have binocular cues, okay? And so it's in the name. It's called binocular cues because it requires two eyes to process this information and get some sense of depth, okay? So it's a particular cue that depends on the use of two eyes in order for us to interpret depth, in order for us to, get some sense of how deep something is, right? So let's talk about this, okay? So one form of binocular cues is retinal disparity, or the single form of it, okay? And so retinal disparity is the difference between two images. And these two images are the images coming from your left eye and your right eye, okay? So your left eye, right, if you close your right eye right now, everybody close your right eye, right? You're seeing a particular image, right? Your nose kind of stops right now. Where it stops for me is it's kind of cutting this part off and I can't see anything to the right, right? Now try closing your left eye, okay? Now you see a different kind of image, right? Now I get more of the right side, but now I'm missing the left. I'm missing some stuff over here off screen in this room. Okay, that's retinal disparity, the difference between those two images that your eye is transmitting. Okay, and so retinal disparity allows us to compare the two images from both our retinas, and then the brain is helping us compute the distance. It allows us to know if if something's really, really close up to our faces or something's kind of further away. Okay, it's only really good for short distances, and you'll see in a minute what's going on with that. Okay, so I want you to try something. I want you to try the floating finger sausages task. Your book talks about it, but I really want you to actually give this a shot so you can really understand what's happening. Okay, so like this image here, point your index fingers towards each other and hold them away from your face. Okay, hold the fingers themselves about a ½ inch apart like this. Okay, leave a little gap there. And then hold them right in front of your nose. Okay, so now close your right eye and, take in the image. Look at your hands and say, how much of my hands can I see? Now close your left eye and do the same thing. Okay, and feel free to pop back and forth, closing your right eye, closing your left eye. Right, so you notice the difference, right? If you close your right eye, you're missing, depending on how far these fingers are from your face, you're missing a chunk of your right hand. And same goes for the left. Okay, you kind of miss that, right? Okay, so that's retinal disparity, right? You're getting two different images. Maybe some of your hands cut off at one point and another part is cut off at another point, right? Depending on which eye you close, okay? So do this, repeat this process where you're looking at two images. Now move your hands further away from your face, okay? Right? Put them way out as long as you can extend your arms. And now look at the image. Now think about what's being cut off. You can see both of your hands, right? You can see most of it, maybe some of your arms getting cut off. Okay, so the retinal disparity is now smaller the further away your hands are. But the retinal disparity is greater. In other words, the two images differ more from each other as you bring your fingers closer to your face. Okay, so what's that telling you? When something's close to your face, your brain interprets the retinal disparity as being great because you have two differing images, two very different images coming in from each of your eyes. And because of that, because it's like, whoa, these are different, you can interpret that as, oh, these fingers are really close to my face, right? This is really close to my face. If the retinal disparity between the two fingers isn't very different, right? That means they're further away from your face because they're way out there. Both your eyes can capture basically the same image. So it must be further away, okay? So retinal disparity is very much helpful for short, but not far distances, okay? So if you want to try the floating finger sausage thing, just to give you a better sense for this as well, instead of kind of blinking your eye back and forth, point your index fingers towards each other, same as before. Hold it in front of your nose, okay? And kind of focus in the distance, okay? So don't focus on your fingers, let them blur out, okay? You should see this floating finger sausage. So your eyes kind of producing this blurred third floating finger right here. And as you pull your fingers further from your face, that tiny floating finger sausage gets smaller and smaller and smaller until it doesn't exist. That helps demonstrate like your images are overlapping so much, right? There's such difference. It's creating this floating finger sausage, but the further and further it is away from your face, the smaller it gets or it disappears. And your eyes have a similar image, okay? So takeaway point, retinal disparity. The closer something is to your face, the much more different the two images from your eyes are going to be, the greater the retinal disparity, in other words, meaning it's closer to you, okay? If the images are similar to one another, the retinal disparity is less, right? There's less disparity, less difference, and that means something's further away from you, okay? I guarantee you this will be on the test. Okay, so let's talk about monocular cues now. So we have binocular cues, which is retinal disparity. This requires two eyes, right? Because you need to calculate the difference between two images from one eye and the other. Monocular cues, as the name implies, only really requires one eye, okay? So as long as you have one eye, you have other cues to depth. And so this is why there are a lot more monocular cues to depth, right? Because in an evolutionary sense, if you happen to lose one eye, at least you've got the other one to help you out. So we're going to talk about all of these, relative motion, height, size, blah, 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 on the next slides. And it'll kind of help explain, right, this fun picture of this woman licking the Leaning Tower of Pisa, but we know, that that's not really what's going on. But maybe if you look briefly, that's a pretty good trick, right? So let's talk about these monocular cues. Relative motion, all it means is that objects beyond some kind of fixation point that you're staring at, like this gentleman right here, any object beyond that fixation point is going to appear to move with you. Okay, so beyond it. So you see these arrows, like this guy's traveling this way, he's going on some train. Anything beyond something he's looking at, all that stuff's going to move with you. Anything in front of the fixation point looks like it's going real fast and it's passing you. It's moving backwards, right? So this is helping us judge, right? This is telling us, basically this is further away. So things further away from you kind of move with you. Things closer to you are going to move behind you. They're going to move past you, okay? Then there's relative height, okay? So this is where, when you're looking at a scene, let's say you're in the forest, right? You might notice that there's like a tiny tree and it's kind of, positioned up high, right? So you've got a tiny tree, or you've got, a tree, I should say, that's got a height up here and one right here. So trees that tend to be further away from us tend to be higher, right? We perceive objects that are higher in our visual field as being further away. So for instance, like the Leaning Tower of Pisa, this is taller than this woman here. We would typically see that as something that's further away, which it is, right? There's grass, there's other things that tell us that. But the relative height tells us this is further away, this is closer to us. Relative size is something I was kind of alluding to. Anything that we see in our visual field that's bigger is usually closer. Things that are smaller tend to be farther away, right? So larger images, right, like this woman right here, is probably closer to us. This is small, and it's a building, so we know it's kind of small and it's tinier definitely than her if you were to cut it out and kind of set them side by side, so we know that's further away. There's interposition. All this means is when one object's in front of another one, we know that one's the closer object, right? Stuff that's being covered up by this bunny here, like this tree, is the thing that's behind it, it's further away. Okay, same thing here. That's why it's kind of crucial to put that ice cream cone right in, here without like kind of being in front of it. That way we can kind of trick people into thinking we're licking this building, right? Interposition. But for instance, her hand is blocking this rail right here, right? So we know that that is further away than her hand. And finally, there's linear perspective. This is simply that when you're looking at parallel lines, when they start to converge or there's less space between them, that's telling us that that's further away, right? Depth Q. But when there's more distance between them, that's closer to us, right? So like a road going into the distance. That's how this picture, which is a two-dimensional, cartoony kind of picture, can give the illusion that this is a road going off into some hills, right? Because it's getting smaller, and so that must be further away in the distance. And lastly, light and shadow usually help us out as well. Obviously, if you see a shadow, that produces some sense of depth, right? So closer objects, like this little graham cracker looking bunny right here, tend to have more texture, more detail, right? So there's more stuff going on. Anything further away, depth, right? Something that's way further out is going to be less detail. And that also gives us a cue. So make sure you know the different types of monocular cues, why they're monocular cues versus our retinal disparity and being a binocular cue. All right, so now let's talk about motion, right? So now we've come from depth, right? Distances of objects and things like that. Now let's look at how we perceive motion, right? When things are moving. So pretty easy rules here. When we're perceiving motion, objects that are shrinking or retreating, that are shrinking, right, that are getting smaller, we tend to perceive that as they're retreating. They're moving away from us. Anything getting bigger tends to be approaching. It's not that it's like actually growing in size, right? So pretty easy peasy motion. There's also some fun kinds of tricks or ways that we can trick our brain to seeing motion. So there's this term known as stroboscopic movement. Okay, so this is a particular form of movement where there's like a rapid series of slightly varying images that keep moving, and that makes it look like there's some motion going on. Okay, so can you think of maybe something where you see rapidly moving images that then produce motion, like somebody raising an arm, right? So for example, a flip book, right? A flip book is a bunch of different images, and you can see this, as long as you see a rapid series of them moving, right, then that gives some illusion of motion. Okay, so that's stroboscopic movement. Think of like a flip book when you think of stroboscopic movement. Okay, so it tricks us into perceiving this kind of motion. So let me give you an example of this. And let's take you to YouTube. Oops, now I kind of moved that. So this is a video, in case any of you are fans of OK Go, where they kind of do some stroboscopic movement to make it look like there's some words in the air. So I'm going to kind of skip ahead. And so these are all people on the ground that coordinated this, and you'll start to see some words coming across in Japanese and also in English at some point. So let's kind of get a little bit forward. Let's play on. So what you can see at the bottom of the screen is it's saying, I won't let you down. Okay, go, right? And it repeats that in Japanese, and there's characters moving around here and there, right? So these are some rapid, like changing images basically, that's giving the illusion that this is like scrolling across your screen. Okay. It's a fun video. I love OK Go. You should totally just watch videos of that and not study. Just kidding. Let's get back to it. Get my little laser pointer again. So that's an example of stroboscopic movement. I won't let you down. There's something related known as the phi phenomena. Okay. And so the phi phenomena is also an illusion of movement, and it's created when two or more adjacent lights blink on and off in quick succession. Okay, you know this as, let's say you're loading a page or something. Maybe you have a Mac and you see that little pinwheel of death, right? And it looks like there's some kind of movement going on in this little wheel of lights. And so all that's going on is these lights are just blinking right next to each other, right? They go on, off, on, off, on, off, on, off, and it gives the illusion that there's some sort of cranking going on. You can also think of like traffic arrows, right? That kind of blink and show some kind of direction of movement. Okay. Okay, so let's talk about a couple last things. This should hopefully pique your interest because we're going to talk about something that I hope you all recognize. So we also, there's also some awesome things going on with our brains. So this is really showing some of these top-down, bottom-up processes, right? So bottom-up, remember, is kind of piecing all this information together, and that's how we see maybe like what this Y looks like, right? But we're also able to maintain perceptual constancy. That is, we're able to maintain the perception of something, right? See somebody as maybe human or human-like, or recognize an actor, for example, even though there are aspects of sensory signal change. In other words, we might see that objects will appear the same even if light conditions change, right? The color or the brightness, right? So somebody maybe has a blue face, but in fact, we can recognize this actor as Sigourney Weaver. Or at different distances and angles, we know that these objects will still be the same. They are what they are. This is, these are people, and even though they've kind of changed for a movie, we tend to still be able to recognize their faces and things, right? They have some blue change to them, but we still recognize them. Okay, so let's explore these more. So this is perceptual constancy. There's color and brightness constancy, and there's shape and size constancy. So we'll talk about them in turn. So let's talk about the dress. Let's watch a video on this notorious dress. So hopefully you all have seen this or heard of reference to it, but basically what happened a few years ago was somebody posted this dress online and people would argue whether it was gold and white or blue and black. Okay, so let's watch a video on that as well.
Alright, so the world has seemingly become utterly divided on this dress. What colors do you see? On the one hand, we have team black and blue. On the other, team white and gold. We asked on Twitter and got hundreds of responses for both white and gold and black and blue. For what it's worth, we both saw black and blue and thought this was a massive prank at first. So how can it be possible for people to see it so differently? It's a phenomenon known as color constancy. Take this cube, for example. The middle square on the top appears to be a shade of brown, while the one on the side looks much more orange. But in actuality, they're both the exact same color. We promise we haven't cheated here or done any trick photography. Instead, our brain looks at the context, sees a shadow, and instantly thinks, oh, shadows make objects appear darker. And so the brain compensates and interprets the square as lighter than it appears, until the shadow is taken away. Back to the dress, and we have a similar situation, except here the context is very arbitrary. We're so close up to the dress that we don't really know its surroundings, and the brain has to make assumptions. People who picture the dress as white have brains which may be interpreting the dress in a blue lit room, for example, as in it's near a window with a bright blue sky. It makes perfect sense then that the white dress would be tinted blue and that the gold color wouldn't really change. On the other hand, the brains of people who see it as black and blue may be interpreting the dress in an artificially lit setting like somewhere with yellow lights. As a result, the brain sees the gold as just a reflection off of the black and believes that the blue has been unaffected. Chances are that this image just happens to be perfectly ambiguous to our brain, meaning it all comes down to individual perception and even how and where you view the image. From a factual standpoint, the dress is blue. In fact, here are some other pictures of it. But this is a beautiful example of how our brains have evolved to interpret the world around us without us even realizing. Want more answers to the world's craziest phenomena? Get the ASAP Science book to feed your curiosity.
Okay, so the black and blue, gold and white dress debacle. So yeah, just like in the video, as they're talking about color constancy, okay? Our ability to see consistent color and changing illumination, okay? But sometimes our brain adjusts based off of shadow and things like that. Like it thinks I need to project a certain kind of color and adjust because I perceive a shadow here. So same with the dress. If you see different pictures of it, if you adjust some of the brightness behind the picture, you might start to see a black and blue dress. Okay, so color constancy is our ability to see this consistent color even in changing illumination. But sometimes the context is going to affect our perception, just like the dress, just like the necker cube. Okay, so this example is the necker cube. They showed a version of it in the video. And so we kind of tend to adjust, or at least our brain is adjusting without us even knowing. Right. So let me give you another example of that. Same thing that he was saying there. We perceive the sides as yellow, right? So we're like, okay, cool. These sides are yellow. You're probably seeing like a darker yellow, but you're interpreting that as yellow. Okay. But because of this, because we're like, oh, this is shaded, this is, kind of a different shading, and this is being lit up, we're going to see the blue dot as different colors. So this one looks like a brighter blue, whereas these look darker, right? But, and I swear I'm doing the same thing that they did. I am not changing this. These are the exact same colors. Okay, it's just where the context in which that they're seen changes it. So yes, we're able to maintain this kind of perceptual constancy, whereby under varying light conditions, we still see the same object, but we can alter our perceptions a little bit depending on the context, right? So it's a fun time there. Shape constancy refers to a very similar thing. Depending on the angle or the distance with which you see an object, you're going to see different shapes of that object, but you still know that object to be what it is. So for example, a door. If you look at a closed door, it's a door. If you look at a door that's slightly ajar, it looks different, right? There's an angle here that's different, but we still know that's the door. Same thing when you open it a little bit wider, it's a different shape, right, compared to these other two images. But despite receiving this kind of different sensory image, right, we're seeing three different images here. We know that this is a door. We know that that's what it is. Okay. So let's move on to the non-visual senses and wrap up sensation and perception. Okay. So first off, let's start with sound. Right, so vision gets a bunch of time because that's one of the main things we use in order to kind of sense the world around us, right? But we have other senses. So let's dive into those. Sound is another biggie. You're going to get a couple of slides on this. So there are some features of sound and sound waves that we should go over, okay? So hearing in general is, audition is the sensor act of hearing. We hear human voices the best, or any sound that kind of sounds similar to them, right? So that's a part of our evolutionary past. We learned, or we evolved to be more attuned to babies' cries and things like that. Okay, so there are a couple of things going on here. Sound waves are produced when we, make some kind of noise, right? It's just molecules moving in the air. They bump into one another, and they create waves of compressed and expanded air ripples. Okay, so that's what's happening. As you hear my voice right now, that's what's going on. So they're characterized by certain similar things to what we went over in vision. There's some kind of overlapping topics, but these molecules have certain characteristics. So there's a frequency that we can measure in hertz, okay, and this tells us the pitch. So the length of that wave tells us different types of sounds, high and low sounds, like the pitch, like, really high pitched voice or somebody who's like really bassy and low down here, right? So low pitches or low hertz um, give you low frequency, right? So, or I should say low frequency or low hertz sounds are going to tell you that it's a low frequency. It's like a bass, right? Versus high pitched sounds, these sound waves tend to be shorter, right? So we're talking about measuring the distance between these humps, basically. Okay, the longer they are, the lower the frequency, right? The lesser the hertz. The smaller they are, the closer they are between each other, the higher the frequency, the higher the pitch. It's a really, really high pitch. Then there's amplitude. Okay, that's the height or the intensity of the wave. Okay. And so that's going to tell you how loud a sound is or how soft a sound is. I think this one's kind of easier to remember along with color, right? The height of for instance, when we perceive color or when we perceive light, right? The height of it tells us something about how bright something is or not. The amplitude here for sound waves is telling us how loud something is, right? When you crank up a dimmer switch or when you crank up a knob, you're going to hear a louder sound. But when you turn it down, right, these shorter waves, it's going to be a softer sound. And this is measured in decibels, right? So 0 is our absolute threshold for hearing sounds as measured in decibels. So 0 decibels is our absolute threshold, okay? And then there's complexity. So sound waves, right, we don't just hear one sound at a time. We can hear many sounds at a time. And so they're going to give us different frequencies and amplitudes and things like that, right? They're going to be high pitch, low pitch, loud or soft. And depending on how complex these sound waves are, tells us something about, is it a pure tone or is it a mix of frequencies? It makes it a bit more complex. Okay. So let's talk about the anatomy of the ear, what's going on in there, how we perceive, or at least how our brain interprets or gets this information, right? So there's the outer ear, this little bit right here. Get my little pointer back, right? So we've got this bit, and what it's doing along with your ear, why it's shaped like that, why it protrudes, is because it's capturing sound to try and funnel it inside your ear. Right? So that's what your outer ear's job is. It's basically just pushing sound inward, or it's trying to capture it and make it go in. So then you have the middle section of your ear. And so these sound waves, right, come in and they hit the eardrum, which is right here. That's why you're not supposed to be sticking Q-tips inside your ear. You might bust the eardrum. That's really important, okay? So sound waves hit that eardrum. It's this fleshy bit. The eardrum is right next to these bones of the middle ear, okay? So these bones are actually touching the eardrum. They're known as the piston. They're comprised of 3 bones. The piston is, I should say. It's the hammer, anvil, and stirrup. These are all part of the piston, okay? This amplifies the vibrations. So your eardrum gets vibrated, right, by these sound molecules, and these bones start to vibrate as well, and they can vibrate more because they're a bit more rigid and they amplify that vibration, okay? So the stirrup, that last bit of bone that's here, is adjacent to the cochlear window. Okay, so we've got the cochlea here, this bluish kind of thing. And so that stirrup is sending the vibrations into the cochlea's oval window, okay, the cochlea membrane. So that's our middle ear. Now we're back at the inner ear, or we're way at the back of the ear into the inner ear. So the cochlea is located in the inner ear. The cochlea is like curled up, okay? And so here's your stirrup, where the stirrup attaches, right? And it's touching or it's hitting the oval window of the cochlea, right? And so the cochlea curls up here. And we'll see that in the next couple slides. Uh, it's filled with fluid and it has little hair cells inside. And so all that vibration, right, from the bone is moving the fluid, which moves the hair cells inside the basilar membrane of the cochlea. Moving these hair cells triggers neural impulses in nearby nerve cells. Okay, so that signal, right? So it's receiving information. It's detecting that certain hairs are kind of moving, and these nerve cells are attached to the cochlea here, and these signals start to go to these nerves, which all kind of form the auditory nerve. Okay. And so this is how we get all that information to our brain. So it's through this system, hits the auditory nerve, right? And these are axons taking that signal up into your brain, into your temporal lobe, so that it can start to interpret the sound, pitch, how loud is it, all that fun stuff. Okay, so let's talk about loudness for a second, right? So it's measured in decibels, as you recall. The way we can tell whether or not you're hearing a whisper versus you're at a concert listening to a rock band and you're really close and probably bursting your eardrums or damaging hair in your cochlea. The way we know that something's louder, right, versus softer is the number of activated hair cells. So all those vibrations, things going into the cochlea, your auditory nerve is detecting like how many cells are being activated. And then it's able to say, okay, there's a crap ton of hairs being activated. You're probably listening to something really loud, right? And then you perceive that. You can perceive like a busy street corner, normal conversation, or maybe somebody shouting at you, right? So you should stick to around 80 decibels or so, just FYI. Try and protect your ears, otherwise they will just go with age. Okay. Another quality of our ears is that we have three-dimensional hearing, okay, stereophonic hearing. In other words, we can hear things around us, right, in 3 dimensions. We can hear stuff all around our head. Most people can. Okay, it's our 2 ears. It's because we have 2 of them that helps us locate sound, right? Because if you hear something coming from the left side, that's your left ear interpreting something louder than your right ear can. And so that's helping us determine where did that come from. That's why you can snap your head in the direction of somebody calling your name. Okay, let's talk about hearing loss. Like I said, take care of your ears. I wish I had popped in earplugs when I went to concerts. I used to think my husband was ridiculous because he brings earplugs with him to the movie theaters and pops them in. And I'm like, well, why are you doing that? And it's because the movie theaters are kind of loud. And now I've actually taken to doing this because I want to preserve my hearing. Anywho, hearing loss. There are a couple of different kinds. We're going to talk about 2 here. Okay, there's sensory neural hearing loss. And this is simply when there's any damage to the cochlear hair cells, excuse me, or the auditory nerve. Okay, if you've damaged the nerve, if you've damaged those cells, you've got a problem. You might start losing your hearing. This one's more common if a type of hearing loss, excuse me. Usually it's hereditary, and also it can be caused by prolonged exposure. So if you're jamming out to that rock band or that music for long periods of time, you're going to start to do some really bad damage to those hair cells, right? Because they're being activated, they're being shaken around. Okay, and that can lead to sensorineural hearing loss. For this, you can get a cochlear implant, okay? And so what happens is they'll put this device and string in a bit of the device into your cochlea, and it acts as hair cells. So then it's kind of taking the place of hair cells, if that's in fact where the problem lies, and helps to transmit that information to your brain. Conduction hearing loss is when you damage any of the mechanisms leading to the cochlea, right? Those bones. The bones are really important, the piston, whatever it is, or maybe you pop an eardrum, right? And so sometimes the eardrum can heal itself, things like that. But what's good for conduction hearing loss are hearing aids. Hearing aids help amplify the vibrations that strike the eardrum. So if you've messed up some kind of bone, things like that, it's going to help to kind of crank it up, okay? Okay, so we've talked about some of the mechanisms, right? We've talked about how we perceive loudness, what happens when you're listening to music way too loud or whatever it is. You're exposed to a lot of loud noises over a period of time, not good for your ears. So let's talk about pitch, right? Whether you hear a really high pitched voice or a really low pitched voice, there's a reason behind that. This is how our brain knows. Okay. It's not just, it is these waves, but there's a specific mechanism to determining this. Okay. So, according to place theory, they put forth this idea. Okay. And we know this to be true. Um, Different pitches, right? High or low pitches, so high voice, low voice, trigger different parts of your cochlea, okay, the basilar membrane, right? So I told you the cochlea is all curled up. This is your cochlea, boop, okay, and it's receiving some information. All the hair cells are in here and they can get shaken up and stuff, right? So what happens is we know that there's a high concentration of high frequency waves at the base of the cochlea. So right around here, okay, you see that there's a really high concentration of these really high frequency waves, right? And so that tells us that we're hearing this kind of high frequency, okay? So that happens at the beginning. We know they're all kind of located there. So the problem with this is it helps explain the high pitch, but not low pitch sounds because there's less concentration of medium or low frequency waves throughout the cochlea. In other words, there's not like a nice, neat concentration of them at the very end or in the middle or something. So if you look at these examples here, medium frequency waves, you'll see more of a spread of them maybe kind of towards the middle in the basilar membrane if you were to stretch out your cochlea, right? And you see here, the low frequency waves are kind of more diffuse. They're everywhere. And so activating one part of the cochlea isn't going to tell you anything about low pitch sounds, okay? They're just a bunch of receptors all over the place, but it's not going to tell you like, oh, because we've activated this one chunk, there's more high pitch or high frequency waves here, we're listening to a high frequency or high pitch sound. So just like with color vision, we have a couple of different theories for hearing high, low, and intermediate pitch, okay? So we just saw place theory. So think about place. Place theory tells you there's a certain place in the cochlea that can tell us that high-pitched sounds are being heard. So now we have frequency theory, which tells us something about low pitch sounds. Okay, so remember, low pitch are those kind of longer waves, right? And so they're going to be a longer distance from one another. Okay, right? So you've got these two humps that are kind of further away from each other. So we know that's low, right? So they're going to kind of hit at different times versus the fast, they'll hit at faster times. Okay. So what happens is your neurons are firing at a certain pace depending on when they're triggered. And so they can be triggered by, they're triggered by these sound waves, right? So if it's a low pitch, they'll get triggered once, twice, versus, a faster, higher pitch where it's like once, twice. It's really quick. So it's the rate of firing. It tends to match the frequency of a tone, okay? And so this is good because low tones then aren't going to make the neurons fire very fast. They can't fire very fast anyways. And so what your brain interprets is how fast your neurons are firing. That really tells you something about low pitches, okay? Why, you might ask? This helps explain low pitch sounds, but neurons can't fire faster than 1,000 times a second, okay? So this is good. This is good for low pitch sounds. That's the range of low pitch anyways when we're measuring that. So we need one last principle that helps explain intermediate stuff in between the lows and the highs, because the rate of firing is still too slow for intermediate sounds, and intermediate sounds also don't cluster like the high-pitched sounds according to place theory, okay? So this is also the fun part. This is in line with frequency theory. they think that it's the combined frequency of these firing neurons that produce the combined frequency of anything greater than 1,000 waves a second, right? So you'll have many hair cells being activated and then start to tell your neurons to fire. And so then it's the combination of how much they fire, right, that tell you something about an intermediate pitch. So if it's a low pitch, you might only get something maybe less than 1,000 times a second, right? Maybe it's 500 times a second. That's how fast your neurons are firing. Your brain interprets that as something low. But if it's maybe going above 1,000 and it detects more hair cells being activated and it's within a range of over 1,000, but not quite a high pitch, then it's detecting some kind of intermediate pitch. Okay. So this volley principle is more about us hearing intermediate sounds. Frequency theory is very similar to it, right? It's just the difference between thinking about the frequency of the combined frequency of the firing neuron cells versus just them, firing at least 1,000 times per second or less. Okay, so we're done with hearing. Now let's get to a couple of other senses. Let's first start with touch. So there are different receptors, just with what we've been seeing with color and hearing, that sense various things. So we can sense pressure, patterns, textures, vibrations, right? Temperature through our thermoreceptors. And so we have these different kinds of receptors to experience touch. We have a more higher dense bit of receptors in the fingertips and lips. If you recall, going back to the homunculus, that weird image of our sensory and motor cortex or cortices, you remember like the mouth had a lot of brain space, right? So we have a lot of receptors in our fingertips, our lips, things like that. And then it's going to take up a lot of space in the brain. So remember, think back to these things. This is how things connect back, right? So why is touch important? Well, there are a couple of things going on. It allows us to communicate different emotions. Emotions are helpful, right? We can detect just the way somebody's feeling, maybe through a hug or things like that. And also there's studies that look at like premature babies. They tend to improve quicker, so they'll be discharged faster when you massage them with your hands, right? Because you might be stimulating blood vessels and things like that. That helps with growth and healing and all sorts of fun stuff. Okay. So let's watch a video that talk a little bit more about the the journey of one girl who doesn't have any experience or sensation of pain.
First, this half hour, an inspiring story about a young girl with a condition so rare that no one, not even experts, know how many people it affects. It's known as CIPA, the inability to feel any physical pain. And that 12-year-old girl is using her diagnosis to make a difference. GMA special contributor Cameron Matheson had a chance to spend some time with her. Here's her story.
What if pain, the thing that parents try hardest to protect their children from, what if that was the thing your child needed most?
Everyone's like, oh, what a good baby you had. But as time went on, the red flags started going up.
From the moment she was born, Ashlyn Blocker didn't cry when she was hungry or had diaper rash, or even when, at just 8 months old, her parents took her to the eye doctor.
When they put the dye in her eye, everyone just kind of gasped. She had a big corneal abrasion across her eye. They were astonished. She wasn't in pain.
It was then her parents got the shocking, devastating news. Their baby couldn't feel any pain.
It was scary because, there weren't very many good outcomes that were involved with this condition. People passing away from appendicitis because they didn't have the warning signs, and bone infections.
I understand that the toddler years were some of the worst, where she would continue to injure herself.
Yeah, the biting, her burning her hands, different things. Tara actually would wrap her hands up with athletic tape. She'd be our little boxer.
Photo after photo document injuries that pained her parents, but not their little girl. What is it like for you to send her out the door every day, knowing what can happen without you there to watch?
It was rough at first.
A medical mystery that for Ashlyn, now 12, I love this room.
Thank you.
I love the color, is just a normal part of life. How would you describe to somebody like me what it feels like to not have any pain?
It's just me. It's all I ever known.
You tell me which finger you feel it on, okay? Okay.
Hoping to learn more about this rare condition, researchers at the University of Florida have been testing Ashlyn since 2004. And a few years ago, were able to pinpoint the exact gene that affects how strongly pain signals are sent to the brain, findings that may one day lead to new pain treatments.
There's a reason for everything, and Ashlyn's here for a reason.
But for today, Ashlyn, just a normal 12-year-old girl who loves pageants and playing in the school band. Woo! And crocheting. It's turned into a fundraising tool for an astonishing family project. All of these you're going to sell, you're going to raise money for the camp.
Yeah. Ashlyn had a dream one night that we started a camp for families like us. I knew instantly what I was meant to do.
We're almost there.
That dream became reality this past November when the family started Camp Painless but Hopeful and hosted 8 families also dealing with this incredibly rare condition. What was it like to see Ashlyn associating, having fun, and playing with other kids?
It was like,
It was an amazing, unforgettable time for sure. I mean, to actually be in a room in presence of someone who knows what we've been through. I mean, know your daily life, your daily struggles, and know you're not alone anymore. I mean, it was just amazing.
Cue the music, please.
Yeah.
Maestro. In exchange for my crochet lessons, Ashlyn made me go back to my Dancing with the Stars days and teach her a waltz.
That's it, you're doing it.
A special moment with a remarkable young girl that I will never forget.
You should be on Dancing with the Stars.
When you daydream about the future, what does that look like now for Ashlyn?
I think it's going to hold everything she wants it to.
Okay, so that was known as the disorder she has is congenital insensitivity to pain.
First, this happened.
And so, right, that is a real eye-opener, I think, because I remember hearing about this disorder a long time ago and thinking that would be kind of cool to not feel pain. But at the same time, that just shows that pain is really important. It's really important to hurt because it's a warning system. It's our first warning system, right? So let's talk a little bit about the mechanism behind all that. So we have what are called nociceptors, or nociceptors, excuse me. And so these are just what I was kind of talking about before. They're just different types of sensory or nerve cell receptors in our skins, in our muscles or organs that detect harmful temperatures, pressures, or chemicals. Okay. And so we have a couple of different kinds. Their signals are interpreted by the brain as some kind of pain, maybe something sharp, a dull burning sensation, something. Okay. And so we have a couple of different kinds. We have, and they vary in size as well. That's going to be key. So for instance, we have A delta fibers, which are good at detecting initial and sharp pain. Okay. Then we also have C fibers that are dull or fibers that detect more dull pain, maybe the longer lasting pain, right? So initially you might prick yourself with a pair of scissors, something sharp, right? And so you feel that initial really painful thing, and then all of a sudden it dulls out a little bit, right? So that's our A and C fibers working differently. Okay, so they're carrying different sensations, pressure, and that kind of pain and that touch. Okay, and so we have these nociceptors, sorry, that have these kinds of differing effects. We also have endorphins. Okay, so your brain can release these neurotransmitters. Sometimes they're known as hormones, depending on what they're being released by. If they're released by a gland, it's a hormone. Released by your brain, we've got endorphins, right? And so we have these endorphins, which are just our body's natural painkiller. Okay, so they activate opiate receptors. They create and this creates an analgesic effect. It blocks our pain receptors. Okay, so it's blocking pain receptors, inhibiting their processes, and that allows us to feel good. That's why we have opiate receptors. That's why we can get addicted to opiates. Okay, so we've got a couple of things going on here. We've got these fibers that can feel various bits of pain. We've got endorphins that can kind of shut them down. But there's also this theory in pain known as gate control theory. And they kind of describe this as being like pain is a two-way street. Okay, so what they mean by that is some of the small fibers, nociceptors, they allow pain signals through. Okay, so there might be some small fibers that allow this initial sharp pain in. Okay, and so these signals, right, like through the small fibers, they encounter gates in the spinal cord. So these gates that are in the spinal cord will determine whether or not the signal is going to get transmitted. So some of them go through, some of them can get through, right? And so depending on the signal, this message will get through, and it depends on a couple of things, like how intense that pain is, the intensity of other signals like pressure, right, burning, stuff like that, and messages you're receiving from the brain, right? Because you're getting some information about pain. It goes and travels up to your brain. You interpret that as being really sharp, really painful, really intense. Your brain's going to start to do something. It'll release endorphins, whatever it is, send messages back down to say, we need to stop this in some kind of way. So then you have larger fibers that sense things like more like pressure, okay? And the large fibers or your brain via endorphins start to inhibit the pain. Okay, so your pain can be reduced in this way, or it can be amplified to try and tell you like that's something dangerous, you should get away from it, right? But maybe after a prolonged exposure to something painful, you want to start the mechanisms to shut down the pain so you don't feel it anymore, right? So these larger fibers might excite inhibitory neurons to inhibit the sensation of pain. And so, for instance, what they think happens is sometimes when you hit yourself, like you stub your toe on the edge of the bed and you're like, darn it, that's the 10 millionth time I've done that. It hurts. There's an initial pain that gets through, but you start to rub it, right? And so what they're thinking is happening is when you rub your toe, you're producing some kind of pressure along that pained toe. That's signaling through your large fibers to the neurons in your brain to close the gate. And so now it's shutting things down and it's not going to let more pain get through. And so that's why we think we rub various injuries. It's to try and help create some pressure to maybe shut down some of those painful signals. In high stress situations, for instance, also endorphins might be released to inhibit some of your pain. Okay. So these are just some mechanisms through gate control theory that explains, when some messages will get through, but some of them will get shut down depending on what kinds of messages are getting through and what we're sensing and what our brain is telling us to do. And maybe even us rubbing our toe, trying to help our brain shut down some of that pain. Okay, so let's talk about a couple of last things regarding pain that we know. There are some interesting biological differences. One of them are that women tend to be more sensitive to pain. They also have a more acute sense of smell and hearing. So that's kind of cool. There are some other psychological influences of pain. So where we put our attention will affect how we experience pain. For instance, you might know that athletes, maybe they break a hand. So you can think of a boxer who punches and breaks bones in his fist, but plays through the pain because they direct their attention towards something else, like winning, towards getting through the round, whatever it is. Another interesting thing is we tend to remember peak and end pain versus how long it's lasting. So remember when it peaked out, like how intense it was, and the end part of our experience of pain, more so than how long it lasted. Okay, so we might remember something that was really painful that lasted a few seconds, but something that, and remember that as being more painful than something that maybe lasted just as painfully but for a long period of time. Okay, or maybe something less painfully for a long period of time. But then that should accumulate to mean more. So what there's a really neat experiment that was conducted where they had participants hold their hand under some ice water for 60 seconds. And ice water is cold. That is cold, right? So they did that for 60 seconds, take it out. Then they were asked to hold their other hand in ice water for 60 seconds. And then they moved from that to another bowl of really, really, really cold water, just not ice water. And they asked them, hold that your hand down, that same hand, for 30 seconds. Okay, so let's say your left hand got 60 seconds of ice water, but then your right hand got 60 seconds of ice water plus 30 seconds of really cold water. Okay, so when they were asked later which one they wanted to repeat, the 60 seconds of ice water or the 60 plus 30, they chose to do the second task where they preferred 90 seconds of pain. Okay, so we tend to not think about duration, right? They preferred that one because the tail end of their experience was less painful. They had a peak amount of pain in the ice water, but then they had less painful experiences in the colder water, right? So even though it lasts longer, that pain, they don't care because it seems that it's less of a pain. Why is this important? Sometimes physicians, for instance, if they're doing a colonoscopy or something, will conduct a procedure and lengthen the discomfort for a minute, but that last minute is going to be less intense. Okay. That way, when they have to come back, if they come back for a repeat colonoscopy, they will remember it as being less painful because that last bit of the procedure was less intense. It was less painful. And so even though it lasted longer, they still perceive that as being less painful. Okay, another interesting thing that's going on here is if we tend to touch objects, that tends to lead to an increase in its value or us wanting it more. Okay, so if you're out shopping, don't pick stuff up if you don't want to buy it later. That's the kind of moral of the story. But even touching something kind of gives us a sense of ownership. We value it more, we might be more likely to buy it. Okay, and finally, in terms of psychological influences, there are also some phantom limb sensations that can occur. So this occurs when an individual is maybe missing an appendage, an arm, a leg, something. Okay. And so our brain produces false senses of pain or perception in that amputated leg or arm. Okay. And so we sense that a hand is there when in fact it's not. And it's just your brain was probably used to sensing something there at one time. And then unfortunately, the hand had to be amputated, whatever the limb. And it's now kind of interpreting, sensations as your hand being there, your hand in pain. Okay, and finally, some socio-cultural influences that occur. We tend to have this thing called social contagion, where the spread of affect or behavior from one crowd participant to another. So when one person feels something, the other person might feel it. And this is linked to empathy. We feel empathetic to people who are in pain. So we might also feel increases in pain sensation. Okay. And finally, there are some cultural expectations that will influence the amount of pain you feel. So for instance, there are some cultures that have higher levels of pain endurance. So Japanese individuals report experiencing less pain. This could be related to the fact that their culture emphasizes more stoicism and hiding pain and emotions. Okay, so they kind of stifle it down a little bit more than some people do, and so they might not experience pain as intensely because they don't express it as much. Okay, so unfortunately, I was going to do a demonstration. I'll bring the strips to class, and maybe we can do a little mini demonstration for taste. But usually, I have people taste a strip, and I ask you what it tastes like, if it is paper or gross. And those of you who taste something that's gross have a sensitivity to bitterness. Okay, and so there's a range of people who sense bitterness. And so some people are known as super tasters who are really sensitive to bitter tastes. Some people are medium tasters who sense some bitterness, but not a lot. And some are non-tasters. They still sense bitterness, just not as extreme. Okay, they're also known as like hypotasters because non-taster is kind of misleading. So what happens is we have these taste buds right on our tongue, and if you have a less dense distribution of them, like this hypotaster does, you don't detect bitterness as much. If you have a more densely distributed taste buds, you might detect bitterness more and more. If you have a really high density of taste buds, then you're like a super taster. You're going to taste some bitter stuff. So we'll try this out in class. So, super tasters. This is a genetically inherited trait. It means that you have denser distribution of taste buds, which are also known as papillae, and you are sensitive to a couple of different chemical compounds, PTC and prop. These are their chemical names, and you will taste them as being bitter. So these strips of paper will have either PTC or prop on them, and that's how you know if you're a super taster. You can either do that, or you can dye your tongue and with like a a non-toxic food safe dye, and count the number of dots that you see, the taste buds. Okay, so this proper PTC, that it's typically a synthetic compound for a thyroid medication, but it's given in such large dosages. When you do this test, it's not a big deal. People who are super tasters or experience some kind of bitterness in response to PTC and prop tend to experience very intense flavors of black coffee, vegetables, fatty or rich foods, and prefer more salt, actually. And it's believed that they're trying to mask some of this bitterness with salt. Okay, why do I bring this up? Because like we talked about before, bitterness tells us something about our food, right? So taste enabled survival in some kind of way. That's why it's important to us. Sweet tells us there's an energy source, right? I talked about donuts in the middle of the desert. You're going to eat that or not. And so that tells us that's some high caloric food. That's something we want, especially in our evolutionary past when we didn't have readily available food sources at every corner, right? Salt tells you something about your physiological processes. So you want salt because it's essential to helping you keep water and electrolyte balances in your body, or the body fluid inside and outside of your cell body, and nerve and muscle function. Okay, sour stuff, bitter stuff tells us that something's toxic or poisonous to us. And finally, there's this last category of taste known as umami. Some people don't really think this is an actual type of taste that is part of our typical tastes that we know tell us something evolutionarily speaking. But some people say that umami is this type of taste that's important because it signals that there's proteins in our food that help us grow and repair tissue. So you can think of like food like fish, shellfish, excuse me, cured meats, mushroom, vegetables, green tea. Those are all kind of earthy tastes. That's umami. And that's supposed to be indicative of good foods for us, stuff that helps us, grow, repair tissue, etc. Okay. So we have more than 200 taste buds. These start to can go away as we get older, so we become less sensitive to food, and pores in our taste buds catch these food chemicals and are able to tell us if they're salty, sweet, etc. And so our taste receptors tend to reproduce every 2 weeks. So don't worry if you've burned a couple off from drinking tea or coffee. They will tend to grow back again. This decreases with age. Okay. In case you don't know who this gentleman is here, that's Takeru Kobayashi. He is a 6-time hot dog eating champ, so I can't imagine what his taste buds are like. And now let's wrap things up with smell. Okay, so smell is an interesting sense in that it's one of the least understood senses in terms of, we know that it provides a function, but at the same time, we don't know a whole lot about the mechanisms because it's hard to study something like that, right? So we've got odor molecules that travel through the air, or they can travel in water like sharks. Sharks can smell. They can detect pretty awesomely, 10 drops of blood, let's say, in an Olympic-sized swimming pool, depending on the species of shark. Okay, so you've got these odor molecules. They're received at the olfactory bulb, so that your air travels through the air, at least in humans, inside your nose, where your receptors on the olfactory bulb are waiting for them, and then they get transmitted from your olfactory bulb to your temporal lobe's primary smell cortex, and it goes to the limbic system. Okay, remember, smell is the only sense that is directly hardwired to our cortex, to our limbic system. It bypasses the thalamus. Our thalamus is part of the limbic system, but it doesn't go through it. It doesn't get filtered in that kind of way. Remember, other parts of your limbic system are the hippocampus, important in episodic memory and emotional memories. The amygdala is important in interpreting emotions. And then you have your thalamus, hypothalamus, okay? And so, right, bypassing the thalamus, we think it's because it's an evolutionarily old sense. So it's existed for a while. And so it's thought that a combination of these receptors trigger different neuron patterns, and this allows us to distinguish odors, right? So there are not a whole lot of olfactory receptors. And so that's why it's thought that it's a combination of receptors that trigger different neural patterns. And that's how we're able to detect so many different smells. So let's talk about some biological implications, right? Let's talk about why it might be important or why smell might be important to us. So we have that direct connection to the brain, right? The frontal lobe, amygdala, other four brain structures. And so it bypasses the thalamus in this way and allows us to have a more direct kind of connection, right? So this can help us really distinguish between things like maybe having compatible mates and stuff like that, right? So it's involved in emotional and social behaviors. And so what we mean by that is we like things that are maybe familiar to us. So babies learn to prefer their mother's scent or their caregiver scent, whomever is around them more. Okay, so they'll show a preference for that. Smell is important in determining compatible mates. So for instance, these individuals down here have conducted some cool studies where they've had men and women score odors of 6 t-shirts that were worn by either men or women, okay? And so people prefer smells different than their own. And usually if they're heterosexual, they prefer the opposite smell, okay, the opposite sex smell. So smell can cue us to having different immune systems, okay? And so we can give out smells that we maybe aren't detecting that tell other people something about our immune systems. And this is important because when you mate with someone, you want to have someone who has a different immune system than your own. That means that you combined, your genes combined, would most likely mix a nice kind of perfect storm of an immune system for your little one that could potentially ward off bad stuff, so they're more likely to survive. So that's also part of it. Okay. And smell also tells us that somebody's in good health, right? Somebody smells bad. That's why maybe we kind of push away. It might indicate some kind of disease, infection, etc., right? If you've ever had any kind of infection, a bad tooth, something like that, you might notice that infections smell. They smell kind of gross, right? And so that's a sign of poor health. We want people who are healthy mates who can reproduce. Right. And so smell preference, like I was kind of talking about with familiarity, tends to be learned. Babies will build preferences for smell. So you could expose them to lavender or, some kind of wintergreen gum or something. And so we tend to build that preference. And preference is going to differ, among countries. And this is how we know that we learn this preference, right? So for example, in the US, the smell of wintergreen, right? If you think about wintergreen gum, that's associated with candies and gums, right? So we like it, we tend to. Maybe some people don't, and that's fine. But most of the time, that's something we associate with gum. Whereas in the UK, people associate wintergreen smell with medicine. Okay, so obviously when you're sick, you take medicine, and that's why we don't like certain tastes of medicines, because we've associated with being sick. We don't like that, right? So they're going to associate that with medicine and being sick, and that's not good. And so their preference, that smell, is going to be different. We're going to prefer wintergreen more in this country, in the US, versus the UK. So let's move on to a couple of things to bring some of these senses together, okay? How they kind of mix and match, and how they work together, or maybe, kind of work with our body. Okay, so first let's talk about sensory interactions. So sensory interactions is when one sense can influence the other. Okay, so what we mean by this is, let's say your smell can alter your perception of how something tastes, right? In other words, it can maybe kind of enhance it. So for sight and sound, for instance, we take in both information about lip movements, right? We can watch somebody talk, and that lip movement might influence what we actually hear, okay? And so a classic example of this is known as the McGurk effect. It's this audio-visual illusion, right? You're watching something and listening to something where we blend hearing and visual and sensory input. So let's watch this video and you'll see what's going on.
Watch this experiment. It's called the McGurk effect. Ba, 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 ba. What do you think he's saying? If you think he's saying da, 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 you are in the grand majority. But now, close your eyes and listen instead of watching. Ba, 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 ba. The voice is saying ba, ba, ba. Now, let's replay it without the sound. Yes, it's true. His lips are saying ga, ga, ga. So how is it that when the lips are saying ga, 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 and the sound says ba, 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 that our brains read da, da, da? The McGurk effect. It's an example of an auditory illusion. It's a great way to show that the accurate perception of information can involve the participation of more than one sensory system. In this case, vision with sound. We call it multimodal perception. The McGurk effect. It's a terrific example of the fact that the senses did not evolve in isolation from each other, but actually work together to help us perceive our world. When multiple senses are stimulated simultaneously, the brain begins to experience an information-rich learning experience and laps it up like ice cream. It encodes more information per unit time, and it remembers that information better too.
Okay. All right, so as shown in the McGurk effect, hopefully you all got that sense. Sometimes it doesn't work as well, but we see mouth movements for ga and the sound for ba that tends to make us perceive da, right? And so there was something going on. There's something about this input of lip movements where maybe you mishear somebody, but like, you know, you're not receiving great auditory information. It's a loud room, but you're looking at their lips. That can help you interpret what they're actually saying, right? We can generally try and do that. Okay. Another example of the sensory interaction is smell and taste. The smell of a drink can enhance its taste. So maybe you smell strawberry, and that might enhance the drink sweetness because you anticipate that strawberries should taste sweet, right? So maybe you have like a lozenge or a hard piece of candy or something that you pop in your mouth and you can smell it. That might actually help to influence the sensation that you experience in the other sense, in your taste. Okay, there are some anomalies though. So there's something called synesthesia, and make sure you're really clear on the differences between like sensory interaction versus synesthesia. Okay, this is when the stimulation in one sense triggers the experience or the perception in another sense. That is, if you're supposed to be tasting something, you instead feel some sort of burning pain. Okay, this isn't like when you're eating a jalapeno. What I mean is, let's say you're supposed to bite into something that's innocuous, like a pickle, and it doesn't burn, right? It's not supposed to be hot or anything. When you bite into it, okay, when you taste it, it might trigger the sense of a color. Okay, so instead of tasting something, you might see the color yellow. Okay, that's what synesthesia is all about, right? So with Ralphie, it tastes like burning. You know, it's the taste. Burning isn't a taste, right? Some people might report something like the number 7, some visual stimuli gives me a salty taste. Okay, so 7 is salty. So this is something that triggers the experience or the perception in another sense where you shouldn't be experiencing something, right? Whereas before with sensory interactions, it's more natural to enhance the taste of something if it smells good, right? Or maybe if it smells bad, then it's going to taste bad to you. Okay, I know what green tastes like. Some people might report that green gives them a taste sensation. Green's not supposed to have a taste sensation. This is known as synesthesia. Okay, and one final thing is this idea of embodied cognition. Again, make sure you understand the difference between sensory interactions synesthesia, and embodied cognition. Okay, so embodied cognition is about how our body's experience on or influences our experience of feelings, attitudes, thoughts, and judgments. In other words, your sensation, your sensory experience of something can influence feelings, attitudes, thoughts, judgments, right? That's different. That's not influencing another sense or anything. That's influencing some kind of attitude maybe you have about something. So studies have shown things like if you hold a warm mug, that might promote social warmth, right? Like you'll be more generous to people, feel closer to them, want to hang out with them more. When you're socially rejected, it looks like you're receiving actual pain signals, like physical pain in your brain. Okay, again, your this influence or this relationship between experiencing pain, but it's also related to a social kind of thing, social rejection. Words on a heavy clipboard might seem weighty, right? So if you're reading words and the clipboard's kind of been weighted down, you might actually feel like they're kind of weighty, right? Like they carry a lot of meaning, in other words. That's what we mean by weighty. Being ignored might make a room seem colder, right? And leaning left physically, like you actually like kind of leaning over, might make you rate your political beliefs more on on the left or liberal spectrum, right? And finally, if a room smells bad, some people were more likely to suspect bad intentions, foul play by others, and because of this kind of play on words, we think something's foul. They might kind of be in this kind of negative headspace and suspect that somebody's there to do them in. Okay, so that's all I've got for you for this sensation and perception wrap up. Okay, make sure you look for the next video on consciousness and sleep. Okay, and then we'll be caught up for Monday. Enjoy, or I hope you enjoyed, your snow day.